Alright everyone, welcome back. This is Peter, UZ Energy Tech Lead, and also ex-CATL Tech Lead, battery tech scientist for more than 10 years. Most of us has just witnessed the launch of the first generation of sodium batteries made by CATL. To my point of view, it could be considered as a major milestone in battery tech development. Since sodium batteries were studied around the same time as lithium batteries, while the commercialized path is way too difficult. However, the recent upsurge of the electrical vehicles and the energy storage using lithium batteries as power source could cause a shortage of the lithium. So a great deal of attention has paid back again to development of sodium batteries, in which sodium is in a large amount, inexpensive, and evenly distributed on Earth. And sodium-ion batteries has many common features with lithium batteries. Therefore, the design concept will be somehow the similar. It should be noted that the launch date is in 2021. Just 30 years ago, in 1991, Sony announced the first generation of the lithium battery, so CATL might deliver some signal to the public. 30 years, giant change. Embrace it. Okay, let's look into what exciting stuff CATL has presented to us. To fabricate a usable battery, there are three major elements: cathode, anode, and electrolyte. In the newly designed sodium batteries, as mentioned, Prussian white and layered material are adopted, and the specific energy density at 160 mAh per gram was achieved, on par with that in the current cathode material of lithium batteries. Even though this number is not that amazing, I personally understand how difficult it is, since there are many choices seems possible. In terms of 2 or 3-dimensional layer transition metal oxide and fluoride, 3-dimensional polyanion compounds, pyrophosphate, silicon-type phosphate, so on and so forth. The design principle is to keep minimum structural change with intercalation, which ensures a reversible intercalation reactions that affect the cycle life. It would be a tough journey to narrow down to a certain Prussian white and layered material. Even though CATL did not mention what exactly the layered material is, they should have found a way to handle the electrochemical stability issues all around. One minor takeaway is Prussian white is not frequently discussed, but I suppose most work can be originated from this group in Sharp laboratories in United States. If you are interested, please go and check. Yes, Professor Goodenough is one of the co-authors of this paper. Seems he's everywhere in the battery world. If I were the sodium battery designer, the very first material of anode I may come up with would be graphite. Since there are too many similar features, electrical behaviors between lithium batteries and sodium batteries, graphite is the most widely used anode for lithium batteries. Unfortunately, researchers have validated the idea a few tens of years ago. The conclusion is no way. Sodium ion hardly intercalates into graphite because of the thermodynamic instability, which is assumed to be the result of the unfavorable mismatch between the graphite structure and the size of sodium ions. In CATL presentation, a size comparison of the lithium and the sodiums can be referred. CATL finally chose hard carbon as an anode. Suppose it is also the choices of many other manufacturers. While CATL improved the specific energy density to up 350 mAh per gram, equivalent to that of graphite. The third major part is electrolyte. Properties needed for sodium batteries are similar to those of lithium batteries. That is to say, chemical stable, electrochemical stable, thermostable, ionically conductivity, low toxicity with low production cost. CATL didn't specify what exactly the electrolyte is, while commonly used sodium chloride and sodium PF6 would be the options. In the presentation video, it is interesting to note that CATL mentioned one system can host 2 types of batteries, that is to say sodium batteries and lithium batteries, together in parallel or in series. merging the merits from both parts. The charging and discharging voltage range of sodium batteries is normally starting from 1 volt to 4 volts, larger than that of lithium batteries. The battery management systems must be powerful enough to set different control boundaries without any conflicts. Another major advantage of sodium batteries can be merged is the 90% capacity retention when discharging at minus 20 degrees Celsius to further improve the power yielding capability at extreme cold conditions. This is originated from the results of fast diffusion of sodium ions in the solid state, and thus resulting fast charging capability. In just 15 minutes, the battery can be charged up to 80% state of charge. CATL sodium batteries gives an overall energy density outcome at 160 watt-hour per kilogram, the top level all over the world. This value is on par with that of current lithium phosphate batteries. But the advantage of the sodium batteries in its low cost and comparable equivalent performances with lithium iron phosphate are attractive for applications like energy storage systems, no matter it is for the residential one or the commercial and the industrial one. I am personally look good into this direction and cannot wait to see the related results. Let me know your thoughts. See you in the comments below. If you like this video, please give a like and a subscribe. I will see you in the next one. Bye.